Hello, AP Chemistry, and welcome to Chapter 14, Chemical Kinetics. A couple of basic things right before we get into the actual kinetics of a reaction, right? Reactions require a collision, right? Meaning that my reactants need to run into one another, right? The collision needs to have enough energy to overcome the activation energy. In addition, they have to collide in the correct orientation. So, kind of like when we were talking about thermochemistry and we talked about entropy, right? Every time we talk about entropy, if we want to justify why one thing has more entropy than another, the discussion has to go back to what does entropy mean, right? Where entropy is three types of motion. How much of those motions does a sample have, right? Likewise, when we talk about reactions, right, and we want to talk about kinetics, this is what it's going to boil down to, right? The kinetics are based on, right, collisions, like do they collide often enough? Can we increase the number of collisions or do we decrease the number of collisions? Can we change the amount of energy per collision? And can we somehow help the orientation of each collision? Okay, and collision is really important. So this is a really simple diagram showing the idea of correct orientation, right? When you get into organic chemistry, for example, right, that's one of the primary things you'll talk about, right? You'll talk about the orientation of orbitals and how one molecule needs to run into another molecule such that the right orbitals run into each other, right? And the discussion gets far more complicated, right? But at its essence, right, in order for a reaction to proceed, right, things have to run into each other in the right way. So for example, here, if these green dots are supposed to form a new thing, right, and these are the parts that need to form a new bond, right, then the green parts need to run into each other, right? And if it collides in any other way, right, then we're not going to get a reaction, right? So despite the collision, despite having enough energy, if this last term is not met, reaction won't proceed, right? So just one of those things you should know, right? And so again, anytime you're going to discuss the effect of concentration or pressure or temperature or whatever, it's going to come back to these three things. Okay, so what is a rate, right? You guys have talked about it in math, you've talked about it in physics, right? But a rate is a change, right, in something per time. In chemical kinetics, when we're talking about a chemical rate, right, we're talking about a change in concentration versus a change in time, okay? For most of our purposes, that is going to be molarity per second, but it doesn't have to be, right? Molarity per second is good when we're talking about aqueous reactions, okay? But for example, if we were talking about a gas phase reaction, we could just as well be talking about pressure per second, right? Because pressure is directly related to moles, which is a measure of how much is present, okay? And the time unit doesn't have to be seconds, right? It depends on the reaction that we're looking at. So whenever we're talking about questions and talking about rates, right, you just need to make sure you're paying attention to the information presented to you, okay? Anytime we have a change in amount versus a change in time, right, that qualifies as a rate, though this is the most common one. And so you'll see here, right, at time 0, so this would be considered T0 or the initial, right? At T0 with our initial concentration, okay, from here to here, over this 50 seconds, this is my rate, right? So we would take this change in concentration over this change in time. Yes? Does that make sense? This difference over this difference gives us this rate. Yes? Likewise, if we were to move on here, right, this change over this change gives us this rate. Okay? All right. Quick note about information that we can extrapolate from graphed data now. Okay? So here if we look, right, we have concentration versus time. Now it's really important that you pay attention to what kind of graph you're looking at. Anytime we have a concentration versus time graph, one of the important things that we can, well, there are a couple, right? But some of the important things that we should take note of, one, instantaneous rates, right? So the rate at a given time, so the rate at t0, or the rate at t100, or the rate at t200, 300, 400, etc., right, is always going to be the slope of the tangent, okay? When I have a concentration versus time graph, the instantaneous rate is the slope of the tangent, okay? So the tangent line, right, you do the triangle, right, rise over run, and that will give you the instantaneous rate at a given time, right? And if we take a look at this graph of concentration versus time, and we'll see that this holds true for most reactions, right, we'll see that the slope of that tangent, what happens to it over time? Right. The slope of the tangent decreases because over time, right, over time for most processes, right, the rate also decreases. And if we think back to our original ideas, right, in that in order for a reaction to occur, we have to have collisions, right? If we think about what happens as this concentration of this goes down, right, as we have less and less of that in solution, there's going to be less of it to run into something else, meaning as we have decreased numbers of collisions, we also get a decreased amount of reaction producing the product, therefore a decreased rate, okay? So anyway, that's one of the things that we should take. So two things, right? So one, concentration versus time graph. One thing we can deduce is instantaneous rates. Two, for most of our reactions, we can also see what happens to our rate over time, okay? All right. And actually, in the next chapter, we're going to talk about what happens in the other part of this graph. But anyway, thank you for listening. Be good, and I will see you soon for the rest of chapter 14. Be good. Bye.